Alright, welcome back everyone. Got another fantastic video for you today. You got Jackie and Neil. Today we're going to be going over force-based testing in the University of Dayton low-speed wind tunnel. Before we do that though, we're going to go ahead and give you an overview of the wind tunnel itself. So I'm sitting in front of the inlet right here. You'll notice we've got this black stuff on front of it. These are screens. What they're used to do is reduce the turbulence intensity going into the wind tunnel. And another important note is that when you're testing, you want to make sure that this whole area is clear. Again, that's for turbulence intensity reasons, and we get nice, smooth, clean flow. So if you come on over here a little bit, you can see the contraction. Our contraction is 16:1. One of the benefits of this is also reduced turbulence intensity, and it also helps speed up the flow. And then this is the plenum. It's an air-sealed room. And we can use this for our open jet test section, so the air is free to flow from inlet to collector. And then back here, we've got our diffuser. And this is, allows the air to slow down so the fan has to do less work. And then finally at the end, this is the fan. It's by Hartzell Propeller. It's 60 horsepower. And so when you're testing, make sure to keep this area clear as well. It prevents blockage effects. And so that's the overview of the UD low-speed wind tunnel. So we'll go on inside the plenum now. All right, when you get in here, you'll see we've got the workstation right behind you. And you'll see that Jackie's closing the door. You want to make sure that that's shut and sealed when you go to do your testing. So as I mentioned before, we got the inlet here, collector here, air flows from inlet to collector. And something very important over here is the Pitot Tube, and it's this blue tube. In order to operate this, what you want to do is you'll hit this power button over here, wait for it to fire up. And then you'll see we've got the readings and everything. What you always want to do is hit this top middle one and then do 0 pressure. And this 0 is the sensor. And so once that's done, you can just hit escape. And now you can see we're basically at 0 meters per second. And then you can throw this back up here. And so this tube actually, or this transducer reader actually connects to this tube, which is our pitot tube. And that's how we measure wind speed velocity. And so this is our test rig. You'll see right here we have a NACA 0012 model mounted, and this model is mounted onto a mount which connects to our ATI gamma sensor, which is a 6 degree of freedom sensor. Currently we have the digital sensor set up. Quick side note, over here in this box is for the Mini 40, which is similar to the ATI gamma sensor. It's also digital. And so underneath that, we've got the Griffin rotary motion stage. And what that allows us to do is change the angle of attack. It has an accuracy of 1/33 of a degree, so that's pretty awesome. And then we also have the Net FT box. This has the calibration matrix for the sensor built into it. And then coming off that, we hook up to the workstation. And then when you want to go ahead and do your testing, there's two things you need to open up. One is the Galil tools, and then the other is the ATI net. So the ATI net, that allows you to get your force data, and then the Galil tools, that allows you to control the motion stage. And so now I'm going to hand it over to Jackie, and he'll go through the rest of the testing setup.
So Jackie here. So one thing that we need to do before the testing is to mounting the model on the sensor. So we have already mounted on there. So one thing you always need to remember is when we're mounting the model, we want to make sure the quarter cord of the model is always mounting at the center of the interface, so that as the quarter cord is the aerodynamic center of the wing, For symmetric airfoil, there will be no pitching moment on the quarter core, and for an asymmetric airfoil, the moment on the quarter core will be constant, so that will be easier for us to record the data if you want to study the pitching moments on the sensor. Another thing we have to always make sure is that the pitot tube has to be placed straight to the flow, so it cannot have any yaw angle. So if you see, it cannot have a yaw angle like this. That's not right. So you have always to make sure the pitot tube is going straight towards the flow so that it measures the right airspeed. And another thing we have to make sure is that the block for the shuttering system is on here so that the wind tunnel won't be shot during the testing. So when we doing the shuttering system operation, we need to remove the block. Anytime other than that, we need to put that thing on there. So here we're gonna introduce the sensor and data collection and how to rotate a rotary stage. So one thing real quick is whenever you're mounting a model on the sensor, you have to make sure the screw goes into the sensor is the right screw, and also the depth of the screw is correct. So if we go to Google, so just search the gamma sensor. So when we go to their website, we're gonna make sure the load on the sensor is not overloading. So the sensor we have for the gamma sensor is the 65-5. So the force on the X and Y axis is 65 newtons, and on the Z axis is 200 newton. And then the torque on all the axes are 5 Newton meter. You have to be very careful when you load the model on the sensor. So you have to do the calculation to see if your maximum expected force will be within the range of the sensor can handle. If it's over the range, you're gonna choose another sensor. So we also have Mini 40, which will have a narrower range of the torque you can measure, which is 2 Newton meter. So you have to be very careful when you do the calculations and to make sure everything is within the range the sensor can measure. So the screw depth for the sensor that goes into the gamma sensor is 5 millimeters. So the screw is M6, and then the depth of the screw can go in is 5 millimeters. For Mini 40, it's M3 screw, and the depth of the screw goes in there is 3 millimeters. So you have to make sure whenever you put the screw in there, check, and then tighten the model. So don't use the round screw, you'll break the sensor and still won't be happy. So now let's go to the computer here. So the ATI software will give you all the force reading and then the torque reading here. So whenever you're mounting a model on there, you're gonna click bias so that all the force is on the bias. And then if you want to load the data, so there's a tab here, say log data, and then go here, click, and then you're gonna save your data to a text file. So let's go ahead to say 0AOA.txt. It has to be a text file. Then click save, and then if you want to collect the data, you can go here and click streaming. So the default sampling rate for the sensor is 100 hertz. So every second it will collect 100 data sample. So usually for our force testing, it takes 5 to 10 seconds of data. So if you go hit see here, this box tells you how many data you're collecting. So let's go ahead and collecting, and then you see the data is collecting, and then you hit stop, and then it will tell you how many data you're collecting. So here is the rotary stage control. The code for the control is for each degree, as Neil mentioned previously, the accuracy for the rotary stage is 1/33 degrees. So if we do PR1, that's 1/33 degrees. So if you want to go 1 degree, it's PR33. And then you type in SP100, which is tell the sensor what's the speed it's going. So SP100 means full speed. And BGA is just telling the sensor, say, hey, hit go. So if you want to repeat your previous 2 commands, you just need to type BGA again. It will repeat the previous command you're typing. If you want to change the angle of attack to the other way, you can do PR -33 and then BGA. So the sensor will rotate back to the degree. So the default we do here, so let's show a big angle here. So you can see the rotor stage rotating, and then the wing of attack is changing. So the default setting for the wing and the measuring is that when we go counterclockwise, it's positive angle of attack, and the clockwise is negative angle of attack. So when you want to go positive angle of attack, we usually do PR negative values. -33 is 1 degree, -66 it's 2 degree. So if you want to go 2 degree and another 2 degree, you just want to do PR -66 and BGA, and then PR -66 again, and then BGA. So that will give you 2 degree and then 2 degree. So that will give you 4 degree. So before you're running the testing, you have to make sure your mounting, your model mounting, doesn't have any interference on your on the splitter plate and on the 3D printed part in the center. So first thing you do is you go here, bias the sensor, and then you push down the splitter plate to check if there's any interference. So you shouldn't read any significant reading on the sensor. So like this, if there's nothing change on the sensor reading, only very minimum change on sensor reading, that means your setup is good. And the second thing is we need to do is to check if there's any interface among all the angle of attack you're doing. So now the wing is at about 20 degrees angle of attack. Let's rotate it back. And we're gonna see here if there's big interference in the sensor. So when it's moving, it gets reading, and when it stops moving, and we can see here, we only got a very minimum force reading here, about 0.12 degree. That's in acceptable range. If your reading is very big, like 1 Newton or 2 Newton, that huge reading on any axis, that means there's interference with your model in the splitter plate or anything else, so that you have to recheck your setup and then make sure there's no interface. So we go bias the sensor. So we want to make sure whenever we started the testing, the wing is always at 0 degree angle of attack. To make sure it's at 0 degree angle of attack, you're gonna go here and turn on the tunnel. So we just run it at very slow speed. Since the wing is a symmetric airfoil, it shouldn't have generated any lift at 0 degree angle of attack. So let's go here and see the sensor. So on the x-axis, it's measuring the drag, and on the y-axis, it's measuring the lift. So now we can see there is lift on the y-axis, so we need to rotate the rotary stage. Let's go ahead and do PR 10. So the force is still changing, is that going down? So we're gonna rotate and keep rotating the rotary stage until there's almost no force on the y-axis, like this. So now you see the reading on the y-axis force is about 0, means that our wing is at 0 degree angle of attack. Now you know your wing is at 0 degree angle of attack. You're gonna shut down the tunnel. Shut down the tunnel, and then you're gonna set up your testing matrix. So what's the angle of attack you wanna do? And then what is your increment of angle of attack, and then everything else. Also, as mentioned previously, you have to bias the Pitot Tube there before you're testing, and you can read the air velocity. So this is the gamma sensor. We can also have a Mini 40 sensor, which is here. So the Mini 40 sensor is a very small sensor when compared to the gamma sensor. It can mount it on this interface and switch on the rotary stage real quick. So the Mini 40 is is a much better sensor. So whenever you want to use the Mini 40 sensor, you have to contact Dr. Sid Ganasekaran for his permission. So if you don't have any permission from Sid, you can only use the gamma sensor for your research or class project. So if you have any question for wind tunnel testing, please contact Dr. Sid, me, or Neil. So we will be around. If we graduated, there will be a wind tunnel technician. And also, again, thanks to Michael Land for making the video, and have fun doing the wind tunnel testing. Good. All right.